Hi, John.
Hi.
Okay, so good. Everything's working. Great. So
Oh, good.
I just got out of another Zoom meeting. So
That's yes. Tell me about it. It's a big feature of life nowadays, isn't it? So,
it is. So
mm.
let me see. So what do I have here from you?
Well, we could just see if I can share a screen from here if I'm allowed to.
Yeah.
So,
So if you have all that stuff, you go ahead and see if you can share.
okay, let me just find. There we go. So here we go. Share screen. Desktop one. Share. Now, if I go full screen with this, yeah. Come on. There we are. Okay. So as long as I minimize you guys, can you see that now?
Yeah, perfect. Perfect.
Okay, good. All right. Well, I'll just escape from that for the time being, and then wait until people come in. At least I'll try to.
Okay. So now I'm gonna be here probably till like 2 or 2:30 because I mentioned like we got cabin fever due to staying like in Fresno the whole last semester in the summer. So we're heading off to the beach with another faculty member and his kids to let our kids play in the sun and sand.
Oh, excellent. Yeah, sounds good.
But
Yeah.
I'm gonna stick around after this. Your talk, right? Your colloquium talk. Roger and Peichun are going to sort of take care of that. But Peichun was also asking for like a CV. So you got your PhD.
Yeah, I just sent that actually. So I sent it by email. So old school stuff.
Oh, you sent it to her?
Yes, I did. Yeah, only about 10 minutes ago though.
Oh, okay. And you sent it to me too. Okay.
Yeah, I did. Yeah.
And now you also sent me like a link to a
yeah, so there's a link to a YouTube video which would be good to show at the end of the talk, I think, if we can manage that. I think it would overtax my internet to do that. So yeah, if you could host it from there, that would be great.
Yeah, let's practice that now. Hold on a second.
Okay, I'm going to stop sharing my screen. Right. Oh, hi, Peichun. How are you?
Hi.
Oh, you're a sergeant now. That's good.
Oh no, these are from the Ross.
Moved up in the ranks or something.
No, these are the fake. Yeah, I should buy the general one.
Yeah. Did you get this? Oops. All right. He's right. Okay.
Okay, so that's working, and so
I think just press play. Yeah. Now you need sound. I don't know.
oh, you guys aren't hearing the sound?
No, no sound. No sound.
Doug, when you can stop share and then go to share again, and you'll see the bottom left corner of the share screen says there's a checkbox for share computer sound.
Okay, well, yeah, we told me about all this too. So stop share. Okay, so now, all right, so say that again, Roger.
You click the share screen button, the big green one at the bottom center. And then when that window pops up, you select which window to share. And at the lower left corner, there's a checkbox for share computer sound.
Okay, hold on a second. So let me get this back up. I'm going to do share screen, and I'm going to click that one. And oh, I got you. Blah, 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 blah. Okay, let's try this again then, shall we?
Okay.
Much better.
Right. Yeah. Good. Yeah.
Okay.
At the heart of everything we do at Los Alamos National Laboratory.
On some of the world's most powerful supercomputers.
That's good.
Yeah. The sound's still very small. Oh, maybe it's my speaker.
It's the way that we understand how the world around us works.
Science is curiosity, asking
That's better too.
Developing solutions so that we can actually have answers to mankind's biggest and most pressing problems.
The ability to work on complex problems.
That works. Yeah. Okay. Good.
All righty. So I will, let me just keep that. Okay. All right. So anyway, I'll be able to share that. And John, I should do that at the end then. Yeah, right?
Yeah, I think that's probably a good idea. Yeah.
Okay. And yeah, so this will run through like 1:30 or so, maybe shorter, maybe a little bit longer. And then,
I think probably shorter unless I got a lot of questions. It's pretty self-explanatory. So yeah, I think I don't know, half an hour, 45 minutes, something like that, depending on how many people there are interested.
we can put this up. So welcome everyone. So our speaker today is Dr. John Singleton. He's actually going to give 2 talks today. He's going to talk about careers at national labs, research opportunities, in particular his national lab, Los Alamos National Lab. And so he got his undergraduate degree at St. John's College in Oxford. And he does PhD at Clarendon Lab, also in Oxford, in '85. He did a postdoctoral stint at Clarendon Lab in Oxford. He's won many awards. He's an APS fellow. He was a reader in physics at the University of Oxford. He's a staff scientist at the High Field Magnet Lab in Nijmegen. So
Nijmegen.
And is currently at or has actually for a long time has been at Los Alamos National Lab, and actually is a long-time collaborator with our own Dr. Pei Chun Ho. So, and I see a lot of students who are here at this point. So, John, take it away.
Okay, I'm going to share my screen and go for the talk. So now, can everyone see that slide? Is that okay?
Yes.
Okay, good. So it's a little bit ironic that I'm giving this talk because Los Alamos National Laboratory is mainly paid for by the Department of Energy, but I'm an employee of the National Science Foundation because I work for the National High Magnetic Field Laboratory. But nevertheless, Los Alamos is a very amazing place to be. You can see in the upper corner here, this is some of the landscape. We're sitting at 7,500 feet above sea level on the edge of an old volcano. And so when you're not working, there's skiing, there's lots of hiking, all sorts of things to do if you like being outdoors. So Los Alamos is famous as the place where nuclear weapons were invented. But since then, the lab has evolved enormously, especially since no one tests nuclear weapons now, or at least no one who is respectable tests nuclear weapons. And so the work has sort of morphed away from constructing things that you then blew up to all sorts of modeling and indeed all sorts of security threats, some of which involve biology, computers, all of these sorts of things. So the lab has a very, very, very wide remit nowadays. So the lab has been in existence actually for over 75 years. As I said, it's evolved into this place which is supposed to intercept or even pre-think, proactively look at threats to the United States of America and to its allies, and basically find how one can get around or prevent these national security issues. There are also research going on into existential threats. There's a large astrophysics department here. There's a large biology division for things like pandemics. And if you've been following the COVID thing, there's been quite a few publications coming out of Los Alamos about it. So really, it's now the site of all sorts of multidisciplinary science. There's technology, biological and engineering capabilities, and there's a lot of computational and special facilities, things for handling biological agents, nuclear materials, high magnetic fields, all sorts of things like that. So it's a very, very sprawling sort of site. It covers 40 square miles. There are many technical areas, which used to be sort of specialized in one particular thing, but the boundaries are rather more blurry nowadays. We've got over 1,000 buildings. There are several special facilities for things like nuclear materials, biological materials, and there are, under normal circumstances, and that means not COVID, there can be up to 13,000 people on site. And the budget that pays for all of this comes mainly from the government, nearly $3 billion per year. So let's move on. So we want to employ lots of good people in STEM subjects. So basically, you know, having a good STEM strength provides this basis for contributing to all sorts of international scale challenges. And I mean, here are some of the ones that are a preoccupation at the moment. There's obviously, given the history, there's the nuclear stockpile, but also there are associated things, not only ensuring that our own stuff is safe and if it ever had to be used, reliable, but also preventing and detecting whether the wrong sort of people are getting hold of nuclear materials. There are things like energy security. A lot of work is done here on alternative sources of energy. So biofuels, for instance, is a big thing. There's modeling of wind turbines. Infrastructure security, stopping brownouts, blackouts, and detecting the sort of software problems, network problems, and things that can cause those. Health, pandemics, future health threats, bioterrorism, all of that sort of thing is covered. And then we want all of this stuff to spill out into the local economy. And so there's a technological transfer division, which oversees things like patents and getting local industries to pick up inventions that we've made in some of these fields. So there's a lot of scrutiny nowadays about, you know, being a good player here. And so we have now these simultaneous excellence aims, which is basically they intersect and it's you know, supposed to permeate the whole of the lab's science and employment culture. So the old mission: design, produce, certify current and future nuclear weapons and reduce global nuclear threats. So excellence in nuclear security, but that's backed up by an enormous amount of science, technology, and engineering. And the remit is very, very wide. You have to be sort of interested in everything if you want to know where potential threats might come from. So there's fundamental science, deliver scientific discovery and technical breakthroughs that support DOE and NNSA missions, and also are publishable in the wider scientific literature. And then also, because we handle a lot of potentially unsafe things like radioactive materials, biological agents, and computer viruses, we want to execute sustained operations that are reliable and responsive to mission needs and basically don't harm anything else. And then finally, this excellence in community relations, that is feeding out into the community across northern New Mexico, making sure that we employ in a very moral sort of way, making sure that discoveries feed out into local industry and benefit the community in New Mexico and throughout the United States. So this core mission that comes from the historical remit of the lab is to ensure the US has a working nuclear deterrent. But of course, you can't blow anything up nowadays. So you basically have to model everything and also test the materials that go into all of these weapons and predict that they would still work if they were ever needed for anything. And this isn't just for threats from other nations. This is for things like, let's suppose you have a rogue asteroid or something that's coming at the Earth. So, you know, it's probably very good to have the capability of unleashing a large amount of energy, but not doing it on Earth particularly. So a lot of this stuff is around modeling and simulation. There's an enormous computing effort on site. Some of the fastest computers in the world have been at Los Alamos. A new one is coming on stream soon. There's all sorts of specialized experiments where you can submit materials that would be used in these weapons to sort of high pressures, high temperatures, and then you can image them. So, for example, here's one of these imaging systems, the DART dual axis X-ray machine. It basically allows you to make a tomographic image in very, very short timescales as something is being compressed or exploded. So these two wings are particle accelerators that produce intense pulsed X-rays, and the target station is here. So all sorts of STEM type careers in modeling, scientific assessment, doing experiments, doing computations and things like that. So again, this is a sort of thing that comes out of this. This has lots of byproducts, this research. So you have ensuring the safety, reliability and performance of the US nuclear stockpile, and into that goes, as I said in the previous slide, physics, design, engineering, production. But out of it come lots of byproducts. You would like to have as a backup to renewables some sort of very sustainable and safe nuclear energy that doesn't produce horrible waste, and which is very secure, which doesn't melt down if there's a tsunami that puts a load of seawater up near you. So sustainable nuclear energy, also resilient materials, which are useful in lots of other industries, and very, very complex calculations that are used in stockpile modeling are also useful for things like energy systems. And this sort of triangle of national security mission, it's sort of not only thinking about future problems, but keeping an eye on other people throughout the world, just to look for things like emerging threats. Because a lot of specialist techniques are required for this sort of work, there are facilities, user facilities, and exceptional pieces of experimental equipment that have accumulated on the site and keep being developed. So for instance, there's this linear accelerator here. It was the first spallation neutron source in the world. It's a proton accelerator, but it has a neutron source at one end, neutron target station. You can do proton radiography. You can do neutron scattering, both inelastic and elastic neutron scattering, using this facility. There are lots of supercomputers on site. So this is the building that houses those. And as well as computation, there's all sorts of science associated with big data going on. For example, if you model a problem in what is effectively about 15 dimensions, how does a human being comprehend what the result means? And so there are things like a holographic room where you can walk through your data, choosing the 3 dimensions and time to take you through 4 possible dimensions of your calculation and things like that. There's the dual axis radiographic hydro test facility, this X-ray source that can be used for very, very fast X-ray pictures of things that are being compressed, exploded, what have you. There's a Center for Integrated Nanotechnologies, which is a user facility. Then there's my place, National High Magnetic Field Laboratory, where we do pulsed power to give big magnetic fields. There's the Chemistry and Metallurgy Research Building, which is a unique, secure laboratory that's evolving so that you can do experiments on materials like plutonium and actinides. There's the Plutonium Processing Facility, and then there are high explosive laboratories, and much, much more. I mean, there's biosciences, and the Human Genome Project had a very, very big input from Los Alamos. So there's sort of various priorities, again, to give you a wide range of the STEM careers that are available here. Material science, we're looking at new materials, new ways of making things, new ways of building things like 3D printing, laser assisted deposition, and what have you. So there's a lot of work on defects and interfaces, a lot of work on extreme environments like stressing things as you deposit them, like putting big magnetic fields on something as you make it, and emergent phenomena. So materials science and condensed matter physics. There's also a lot of things involved in electrical engineering, mechanical engineering. So looking for nuclear detonation, modeling it, looking for nuclear processing, movement of nuclear materials, weaponization of things. So there's satellite observations. There are all sorts of monitoring devices that you probably wouldn't even know were there at various ports and things throughout the world. And then also looking at natural and anthropogenic phenomena, which can look like nuclear weapons or are very similar to nuclear weapons, like, for instance, supernova. Then it's very important to know what you're modeling. So there's a big effort in nuclear and particle physics. There are nuclear science and engineering divisions. There's accelerator science and technology divisions that feed into new accelerators that are being built around the world. There's good old weapons design, manufacturing and analysis, keeping the deterrent that exists, you know, in some sort of reliable working state. And then information is an enormous part of the remit of the lab now. So information technology, threats from things like viruses, networks being taken over and what have you, and enormous scale of data science. So all of that is a remit of the lab as well. And then finally, there's all sorts of human interactions with things. This is biological, with machines, with computations and things like that. So for example, a very economical NMR system came out of this that can be used for imaging brains in places where there's poor infrastructure, poor electrical supplies and things like that. This keeps evolving. The lab keeps evolving as time goes on. For example, with the supercomputing, started off with one of the first craze, and then things get bigger and faster and what have you. Now the target is exascale computing, using perhaps even dispersed cloud-style computing, optimized use of processing and things like that, so that you can model very, very big things, not just for weapons, but also phenomena in astrophysics and condensed matter physics, real-time crystallization of solids and things like that. The experiments used to be underground testing, but now these are experiments in characterizing the materials and how they would react to under conditions which were used in weapons. And then in future, there's going to be a whole effort put into extreme conditions on condensed matter physics systems. So there's a thing called Damask, which is going to be high magnetic fields, high pressures, short time scales, high temperatures, high energies, imaging materials that are subjected to all of these things and see how they react, see what comes out of it. And nowadays, of course, there's a lot less manufacturing. Instead, it's a kind of maintenance of the plutonium that's around. So here's some sort of expansions of some of these things, just to show you again the range of STEM opportunities there are here. So stockpile stewardship, the thing of ensuring that the weapons would work if you ever had to use them. There's a lot of fluid dynamics research in there. There's also a lot of very intensive supercomputer modeling and simulation, which has lots of spin-offs into other areas. Things like global security. If you came out of particle physics, for instance, we use muon tomography to look for things that might be hidden in containers like this, imaging other people's reactors that have gone wrong, and also surveying old architecture to see why buildings like this church dome in Florence are falling down. There's a lot of satellite work done, basically watching what's going on the Earth, watching what's going on in outer space, things like supernovae, gamma ray bursts, and what have you. For instance, Los Alamos has provided quite a lot of the instruments that are on the Mars rovers that are out there at the moment. There's a guy called Roger Veens who's been a designer of a lot of the cameras and chemical analysis kits that are on the Mars rovers. And then moving over into energy security, this ranges from computers, modeling networks, modeling problems in controlling networks, modeling networks where some unpredictable thing can take part of your network out. And there's electrical engineering, of course. And then chemistry, materials science, and things feed into projects like developing accident-tolerant nuclear fuel. Here's another instance of the sort of thing that goes on spanning particle physics through to materials science and computation. So for example, there's laser-assisted deposition going on. At the same time, we're looking at proton radiography to see what's happening kinetically with very short time scales. We have X-ray sources that can also probe surfaces going down. So you get an unrivaled understanding of the sort of microstructure you get when you're using these modern deposition methods. And practical things come out of this. In fact, you know, if you actually damage material that's being deposited by these means, it strengthens it quite a bit, which has, for instance, led to a spin-off into a new form of gas bottle. We're thinking here of future hydrogen-powered vehicles and things like that, so making stronger, safer gas bottles for those. And this is in parallel with all sorts of modeling that goes on. There's modeling of the deposition process. There's modeling at a sort of micron scale to look at the microstructure. There's modeling in a more quantum mechanical sort of fashion, looking at the underlying bonding and things that gives rise to this. So this is sort of micron scale, nanoscale. And then there's even dynamical modeling of how all of this feeds into how the material behaves under stress and what have you. So this ranges from materials science, metallurgy, condensed matter physics. There's particle physics in the infrastructure used for imaging these things. There's a lot of computation here, hardcore computational work to model all of this stuff as well. So it's a wide range of skills that are here. We are not just on site and not just doing nuclear stuff. There are a lot of collaborations that the lab's expertise allows us to take part in. So there are things like risk assessments, therefore, you know, just thinking of the worst possible thing that could happen to your infrastructure, to your population. There's carbon capture. There's a lot of stuff to do with biofuels from our chemistry and biological divisions. And some of this involves making demonstration facilities here and elsewhere. We've got a grid modernization consortium, which is to do with energy security. If something takes out a large portion of our grid, a natural disaster or worsening weather due to climate change, you want the rest of it to survive. You want the bit that's damaged to come up as fast as possible. And then there's work into hydrogen fuel cells as well. So we have quite a steady budget which grows. It's almost 3 billion, that should say. Okay, that should be a comma there. Sorry about that. A lot of this is just keeping an eye on the weapons program and other people's weapons programs. But much of this, rest of this, is pure science stuff that gets published in the open literature as well. And then there are things like looking for existential threats and what have you. The lab is continuing to do a lot of hiring. This is a graph showing the number of hires per year in the gold color. Attrition is people retiring, taking early retirement, moving elsewhere, and what have you. And you can see that the hiring in recent years has been outpacing the attrition. So the overall head count, which is to the right side, is going up steadily as a function of time. And also the hiring, a lot of the hiring for scientists and STEM people is done via studentships and postdocs. For example, if you're working in nuclear engineering, you can be hired straight on after your studentship, and the lab will put you through a master's program. Postdocs, this is now creeping up again. So there are lots of postdocs, and generally after these, there's some form of conversion into staff if you've done okay. The diversity, we're working on this to try to get as diverse population as possible. There's a big push in the wake of the APS-ID initiative. As you can see at the moment, we're kind of around the average of the DOE national labs, but we're hoping to improve on that. But anyway, lots of recruiting going on. So there are lots of potential for actually being employed here. There are also many opportunities to do summer internships, REUs, things like that. At Los Alamos, there's a web page, which I'm going to list on the next slide for those. So student programs, you can come and work here for the summer. It's a bit impacted by COVID at the moment, but we did manage to have some students on site or working from home over the last summer. There's postdoctoral programs. If you're finishing up on a PhD, you know, this would be a good point for recruitment. We also got lots of outreach to involve other types of places with our research. So there's this Security Education Center. Basically, this is promoting new educational programs, which then feed into the student programs. There's a consortium, which helps us work with more and more universities, especially ones in New Mexico. So we provide them with unique facilities. They provide us with students, employees, postdocs, and things like that. And then there's this Center for Innovation, which tech transfers things out into the community so that we can perhaps invigorate US industry. So this is my summary. There's lots and lots of areas involved in this: energy security, handling nuclear materials, doing things like equipping the Mars rover, doing hardcore spectroscopic experiments and things. So there's room in here for all sorts of multidisciplinary science. There's lots of jobs for scientists, technologists, and engineers, computational people, and specialized things like biosciences and nuclear facilities. So we're interested in getting an agile, responsive, and innovative workforce, young people, people from diverse backgrounds, people with lots of different experiences. And that is what we're aiming to do and build on over the next few years. So for the studentships, REUs and things like that, down here, www.lanl.gov. There are job opportunities, studentship opportunities, and things like that advertised on here. There's connection to science reports on what we're doing with science stories coming out of the lab, links to latest publications and stuff. So if any of this has interested you as a possible career, have a look on here. Have a look at the summer internships. You can also look at the National High Magnetic Field Labs internships, which operate over the holidays as well. And we have labs as well as at Los Alamos in Tallahassee, Florida, and Gainesville. All right, so there we are.
Oh, hold on, let me start my video. So thanks a lot, John. And actually, before we go on to questions and answers, do you want me to run the video?
Yes, if you could run the video, that would be great. Thanks. Yeah, I'll mute myself. That's going on.
Let me do a share screen. Okay, here. Hold on. Let me do it. Hold on. Before I do that, let me do share screen and make sure. Okay, I'm sharing my audio. Good. Are you guys seeing the beginning of the video? Are you guys seeing the beginning?
Yes.
Okay. All right. So stop me if there's anything.
At the heart of everything we do at Los Alamos National Laboratory is science. Pure and simple. Well, maybe not so simple. The diversity of scientific endeavor at Los Alamos is amazing. National security science requires basic research.
We have experts here from all over the world, and we also collaborate globally. This diversity of scientific thought has always been the laboratory's greatest strength.
The Manhattan Project brought together a large number of experts in various technical fields from all around the world to solve a very complex problem. Today, we rely even more on that level of expertise for certifying the safety of the nation's nuclear stockpile through very complex simulations on some of the world's most powerful supercomputers.
Computational simulations are vital to the work that we do here at the laboratory. There are many things that we're interested in that we can't actually test with a physical experiment. We need to use the best science and engineering that we have to protect the nation.
We're trying to solve problems through the pursuit of science with the hope that our science makes the world a better place. More than that, we can make it a brighter, a safer, a more stable place.
A national lab is always thinking about the biggest challenges that we have and how we come about solving those challenges.
Science here at Los Alamos is definitely not a one-person venture.
The collaborative nature of Los Alamos allows for experts in all fields of science to come together to solve big problems.
Problems that are too big for one person working in isolation to solve.
There's a lot of really good science here for a variety of global security, national security interests, because that's what needs to be done.
We like to leverage our science capabilities to inform our national security work, and then at the same time, that national security work bolsters our science capability.
And because of that, we're able to work on new discoveries and different science that can't be done anywhere else.
Science is the ultimate exploration for knowledge. It's the way that we understand how the world around us works.
Science is curiosity, asking questions, developing solutions, so that we can actually have answers to mankind's biggest and most pressing problems.
The ability to work on complex problems, help solve them in the national interest, is one of the most rewarding things a scientist could ask for.
Our science is what prepares us to face the uncertainties of tomorrow. It allows us to achieve things that are right now only in people's dreams.
Thank you very much, Doug. Thank you.
All right. Thanks a lot. That was great. So now let's give the students a chance to ask any questions. So just unmute yourself and ask away.
Stunned silence.
Yeah.
So I have a question.
Mm-hmm.
So I came in late. I'm not sure if you have mentioned this or not. Is there like related to the researches and studies more related to like weapons, or because there was a lot of information about like nuclear? I was confused.
Well, so that is part of the lab's activities, because someone has to keep an eye on whether nuclear weapons might work in the future and who else might be making nuclear weapons and things. But the spin-off from that is there's an enormous amount of fundamental science done at the lab. So, there's a lot of work done in very pure condensed matter physics experiments and condensed matter theory. There's a lot of work done in astronomy, astrophysics, things like satellite flying, the Mars lander. All of these things have Los Alamos input. So it's basically, the lab its mission is to sort of look for existential threats, but to be good at spotting existential threats before it's too late, you supposedly have to know about virtually everything. And so the lab does a bit of everything. There's biosciences, there's a lot of computational work, there's a lot of technology and engineering. So although, the original core mission of the lab was nuclear weapons, there's many other things go on besides that now. And a lot of that is pure science.
Has anyone ever like done research or started research in like computationally, like simulation for climate change and global warming?
Yes, there's an enormous program at Los Alamos doing that. So one of my colleagues is in charge of that, and they do a lot of modeling of atmospheric dynamics. They do a lot of modeling of water and sea dynamics and interactions between the atmosphere. They also have many monitoring experiments which are looking at things like dispersion of particulates. They monitor things like the carbon being liberated from forest fires. They look at global pollution and how it travels. They have airborne experiments, satellite experiments and stuff. Yes, that's a big component, because climate change is an existential threat. And so we need to be interested in it.
And also, like, do you aware if like has there been any study in modeling the fires of like that are going on in the forests?
Yes, so that's a very big part of the climate. So, for example, we had a big fire in Los Alamos in the year 2000, and a lot of modeling has gone on about how that spread, why it spread. There's a group here which is monitoring the wildfires in California and in Portugal, and they're trying to understand how the climate dynamics on a day-to-day basis helps with the spreading of the fire, the sort of biological pressure that the fires put on the environment, and you know, the sort of feedback mechanisms like fires make, you know, contribute to climate change themselves by liberating carbon dioxide into the atmosphere. So yes, there's a lot of that work going on.
And also one last question that I have. So I'm an undergrad that have like already started learning about like researches in computational field, and I wanted to know like at what level can someone start internship? Like, do I need to be a grad student or like?
No, you can do it as an undergraduate. In fact, if you're in the, you know, if you know about this, you can even start while you're a senior at high school. So just go to that website that was on my last slide, which is www.lanl.gov, and that has opportunities for internships at all sorts of levels in it. So, you know, I've employed people who are computer science majors, and usually their summer internships have you know, allowed them to learn maybe languages or procedures or math that they're not doing as part of their computer science degrees. I've also employed, you know, physics students, undergraduates, and engineering undergraduates to do computational work, and they've learned new stuff that they hadn't thought about before. So yes, there are lots of opportunities for undergrads.
Okay, interesting. Thank you.
Mm-hmm.
So more questions? Okay, actually, well, so you guys think about actually, so John, I have a question. So is it, to get a summer internship or research position at Los Alamos, is there a citizenship requirement, or like what are the sort of like, aside from the academic requirements, what are the other potential requirements?
No, so a lot of the internships can be done by people who do not have US citizenship, because there's a large amount of work that's carried out here that is just devoted towards publishing papers and doing fundamental science. So I mean, for instance, my group, the Magnet Lab, we usually have 5 or 6 students over the summer, and several of them have been from European countries or Korea or Japan, that sort of thing, India. So as long as you don't want to do work that's actually real core nuclear weapons work, then there's no real problem with any other nationality. So qualifications wise, you're supposed to be running a GPA that's above 3 in your course, and if it drops below 3, there will be a review of what's been going on, and sometimes then, you know, students are told improve your GPA before you come back.
Okay, good. Okay, so I'll talk a little bit more to give the students time to think. So we're recording this. So John, if you don't mind, we're gonna post this on our colloquium website, and I'll advertise it. And you also send me the slides to the talk. So I'm assuming that's okay to post those two along with there. So
if they're going to be posted, I need to get an additional review done on them. But you could post us talking, certainly. But I'll be able to do that within about a week or something.
Okay. So my plan was this thing that we're recording now, I was going to post. So that's okay, and you don't need any review.
Yeah, that's fine. Yeah.
Okay. I mean, so the thing is,
it's a kind of it's a sort of default thing. It's just a bit of paperwork that you have to do if you put anything out from the lab. So the movie is completely fine. It's just my slides need to be reviewed. So for if they go on the internet. So yeah.
Okay. Well, so you know what? Actually, I think if anyone comes and watches the recording, they can get the various links that are important from there. So I mean,
Yeah.
okay, let me just say, if it's a big hassle to get the approval to post your slides, then don't worry. But
no, it's not a big hassle. No.
Okay. So yeah, so let's do that. So, you know, just ask for the approval, and then once it's given, then just shoot me an email and we'll post your slides, because I noticed the slides had a lot of links and emails and stuff like that that would be useful for the students looking.
Yeah, yeah. The main thing is www.lanl.gov. You can get to everything from there.
Okay.
Yeah, well, everything that that you're allowed to get to from there. Yeah.
Okay. So have you guys any questions from the students? No. Okay. Well, if not, thanks for coming. Thanks to Dr. Singleton for an excellent talk. And let me remind you, at 3 o'clock, he's going to be giving a colloquium on Majorana fermions and their use in condensed matter physics. This is a hot topic, both in condensed matter physics and actually particle physics as well. So please do show up for that. That will also be recorded. All right, thanks a lot.
Thank you.
Oh, by the way, Doug, do I need to do anything, or I just being a co-host? That's sufficient.
Oh, what's a okay?
Hey, Doug.